right, time to start. So we'll probably get through chapter 2 today. Chapters 1 and 2 are pretty simple, so we're going to slow down a bit, after this, of course. But these are kind of easier chapters. And this chapter reminds me of a time, this is back when I worked at UH Manoa, and there was, on Fridays, there were frequently drinking events, different departments, and there was this one guy, he came up to me, he's like, "Oh, you're a chemist." He's like, "I don't believe in atoms." I was like, "All right, this is my moment to shine." I'm like, if I can convince this guy that atoms do exist. And so I went over what we're going to talk about in the beginning of this lecture, and law of conservation of mass, definite proportions, multiple proportions, and scanning tunneling microscopy. And I was like, I can convince this guy I'll be a great teacher. And then it turns out he was angry about pesticide use or something like that, and decided to say, I believe in atoms. I just don't like how it's used in pesticides and stuff. I'm like, all right, well, of course, I guess a lot of things make more sense after a few beers, but who knows? So hopefully today I will convince you that atoms do exist. Most everyone thinks that atoms exist, though. I don't know too many people. I've only had in my entire teaching career of 13 years so far that I had one student that never heard of atoms. So everyone else seems to have heard of atoms and or more or less believes it to be true. What's nice about today is that we can see them. Here are some images of atoms. And so those little green and blue dots on there are atoms. And this is a scanning tunneling microscope. I say image because you can't see atoms. So for instance, a hydrogen atom. A violet photon at 400 nanometers, you can fit about 800 hydrogen atoms in between that. A 700 nanometer photon, red light, you can fit about 1,400 hydrogen atoms in that. So even with the world's most powerful optical microscope, you won't be able to see atoms using light. You have to image them, and you can image them using there's two ways you can image them. Scanning tunneling microscope, another one's called an atomic force microscope, AFM. So here the STM, the yellow looks like a yellow bunch of grapes. Those are tungsten atoms. So you take a tungsten wire and you make it really, really tight there, and then the balls on the surface, the balls on the surface here, those are atoms. They are more or less spherical. They look like tennis balls in this image. But then if you look at this image, the real image, they look kind of like a pimple. And the reason for that is that when you have this, and the way a scanning tunneling microscope works, you put a potential behind it, and when there's an electron density, it can jump up into the wire. But the thing is that and the way they work is you have a surface, and the wire scans back and forth like this. If you have this other atom here on the side, you can get a signal from it from going over the atom. So what would be a perfect sphere actually ends up being like a pimple kind of thing when the scan is actually going on. So you see that atomic force microscope, I mentioned them. It looks like this. It's like an arm with a needle point on it, and they take a laser and they shine off it, and they detect the laser, and then they move the needle over. And whenever there's a rise or bump, you can get the rise or bump. Then it'll go down the arm, and then you can get the image from the light coming in and off, and you look at where the laser pulse moves. And with the AFM, atomic force microscope, bumping around the surface, you then can map what the surface looks like. So the other thing, AFMs look like candy corn, kind of. They're really sharp. They're really sharp-looking images. STM, scanning tunneling microscopes, they look like pimples. That's another way you can tell the difference. Okay. So, but I mean, can you imagine if we didn't accept atomic theory? This would be a hard sell, because you're like, okay, all matter. I mean, not all matter is made of atoms. I mean, like pions and muons and neutrinos, those are matter. They're not made of atoms. But all the matter that we really care about, like iPads and ourselves and staplers, the air, planets, the sun, they're made of atomic matter. but like, okay, everything is made of atoms. You can't see them, and but they're made of everything, and each element is smallest unit is an atom. Like, yeah, right. Come on, man. So how do you prove that? And this is how we proved it. Well, this Dalton is the first guy that came up with the idea. Well, not Dalton, not necessarily. The ancient Greeks did. They thought there were four types: the earth, wind, fire, water, four atoms, and they were solid, indestructible spheres. Same thing with Dalton. He thought they were solid, indestructible spheres, and he came up by these 3 points: the law of conservation of mass, the law of definite proportions, and the law of multiple proportions. He came up with atomic theory from these points. So conservation of mass states, this illustrates this in definite proportions, that for any chemical or physical process, matter is conserved. The break in that rule, of course, is E equals mc squared. Matter and energy are interchangeable. So you can break that in a nuclear process. So here we have 19.6 grams of sodium and chlorine react to form the same mass, sodium chloride. So matter is conserved here. This is the law of definite proportions, that compounds are formed from elements and defined and definite in the same proportions. So like for water, H2O water, it's 1 to 9. So 1 part hydrogen by mass and 9 parts oxygen by mass will form H2O water. And if I have 2 grams of hydrogen and 9 grams of oxygen, so it's a 1 to 9, I will get 10 grams of water plus 1 gram of hydrogen excess. So it doesn't matter how much you have. If you have excess, you'll make the same compound, but then you'll have excess. That's the law of definite proportions. Law of multiple proportions is you can have 2 or more elements, and you can make, if you can make different compounds from them, they can make different compounds, but they're in different proportions. But the proportions are also definite, though. So for instance, water, you can form water from hydrogen and oxygen. You can also make hydrogen peroxide, H2O2, in a ratio of 1 to 16. So 1 gram of water, 16 grams of oxygen can make 17 grams of peroxide. Also, 1 gram of hydrogen, 9 grams of oxygen can make water. So, but I mean, each one is at those specific proportions, but for 2 or more elements, you can get multiple. So that's multiple proportions. Dalton said, what's going on here is that elements are made of atoms, and they're all the same, they're hard spheres, and then that explains all these things. So Dalton came up with that, and then we tried different things. This is a brief history lesson. I'm not going to go too deep into the history. Cathode rays were discovered. A cathode ray is just an electron beam. So like an old television set or an old, maybe you've heard of a cathode ray tube, CRT screen. Televisions were this way, so were computer monitors. Televisions and monitors tend to be liquid crystal displays now, so they're not cathode ray, but this one here, that's an LCD, so is this. This is a projector, it's different. The way old TVs worked is you had a filament, so usually a piece of tungsten, and you ran electricity through it, and some electrons would spit off of it. And you had 2 plates, and you put a negative charge on them that would shoot the electrons down the cathode ray tube, and then they would, using magnets, you would bend the electrons, and then it hit the screen, which was just it was a honeycomb. For black and white, it was just black and white pixels, and then for a color television, it was red, blue, and green, like a honeycomb pattern, and you could get colors that way. So, but of course now instead we use liquid crystals. They're long organic molecules that we can put and do different colors. So depending on how we rotate the light, we can apply electricity. We can get colors from that. So, but that's the old way we got TV screens to work. And we also then figured out charge and mass of the electron. We found out, so electrons existed, so there's something, atoms are made of something because we can rip them apart, so they're not just hard and spherical. And then we came up with the plum pudding model. So here is the plum pudding model of the atom, and it's kind of like the blueberry muffin model, as I like to say, for contemporary American society, because plum pudding is more British. So a blueberry muffin is like like a cupcake kind of thing, the white cake, and then there's blueberries in it. So same idea. The electron is this big ball of positive charge, and then you have electrons floating around this big ball of positive charge, and it's very diffuse. So that's the plum pudding model. Then Rutherford came along, and he wanted to see, okay, let's talk about this plum pudding model. He thought that he could shoot radiation at it, and we would have radiation go all the way through. So he could either prove the plum pudding model, or he could prove Dalton correct. If atoms were all hard and spherical, if you shot radiation at it, it would all bounce off. Okay, so what do I mean by shooting radiation? So the smoke detectors, we have smoke detectors in this room. There's one right there. The way that these work is there's a laser that goes across it, and if smoke comes and blocks the laser beam, it will set off the alarm. The ones that I have at home are much cheaper than this because this comes with a subscription to like a bunch of services and that kind of thing. The one I have at home it's just the ones you buy from Costco, right? They're about this big, and they stick to the ceiling, and if the batteries go dead, they start to chirp. So the way that those work is much similar to Rutherford's experiments. There is a radioactive source. In the case of the smoke detectors and most everyone's smoke detectors, it's a radioactive element called americium. It's in there, and that emits an alpha particle. And so you have a source, and it's just a metal casing that has a hole in it. So the radiation is spitting everywhere, but it just spits through the hole because it's blocked everywhere else. So radiation spits out, and you have a detector up here that if smoke goes through, it gets charged by the ionizing radiation. Then if charged particles hits the detector, the smoke alarm goes off. So same idea Rutherford did. He took a radioactive source, encased it in lead, put a hole in it so you can get a beam of radiation coming out of it. Took a piece of gold. Gold you can hammer very, very thin. And this is in like the 19th century, by the way. So this is before computers and that kind of thing. So you can take a piece of gold, you can hammer it really thin, like with gold leaf. He put gold is an element. It's made of matter. It's made of atoms. So he put the gold foil here, and he shot radiation at it. And he thought, okay, if all the radiation goes through, we'll prove the plum pudding model. If it bounces off everywhere else, they'll prove Dalton's theory right. He was expecting the plum pudding model to be correct. He also did is he took one of his graduate students, and he like the clickers that you have for like events. People, if you ever walk in, someone like click, click, click. I mean, they had those back in the 19th century. So he gave his grad student that, and he put him in the dark. And I don't know what kind of screen he used. Certain screens, when it gets hit by radiation, it flashes. Phosphor does that. Cesium iodide does it. I'm not sure exactly which material he used. But either way, there are certain screens that get hit by any type of radiation. They flash. And so he put one of those materials there, and he told the grad students, all right, I want you to stand here and look at the screen. Every time you see a flash, use the clicker, and then when you're done, record the data, and then take a step over, and then do that, and then keep on going, and so on. It took the grad student about 2 weeks to gather all the data, and then compile it, and then he gave it to Rutherford. Rutherford looked at it and says, this is completely wrong. I want you to do this again. So the grad student repeat the process, 2 weeks in the dark with a clicker, kind of thing. And this is before Excel, kind of thing. So you're just writing it down with a pencil, probably a pen, or maybe a ball, like a dipping pen or something like that, with a feather quill, who knows. Writing on parchment, giving it to Professor Rutherford, and he's second time around, nope, still not good enough. And the grad student then goes, hey, look, Professor Rutherford, you're here doing professional duties, so you're smoking your pipe in your tweed jacket, you're drinking coffee with your colleague. I've been doing this for a month now, and this is right. This is absolutely right, and if you don't believe me, do it yourself, kind of thing. So Rutherford thought, like, maybe this grad student is right, and looking at data, he came up with this idea, was the nuclear atom. The idea that, so unlike the plum pudding model here, it's just very diffuse, that the atom has an electron cloud around it, but the electron cloud has essentially no mass to it. but all the mass is concentrated in the center of the atom, in the nucleus. And this is closest to our current model. The current model for the atom is the quantum mechanical model, which we will talk much more in depth in Chapter 7. We're also going to talk about some things today about like the periodic table. We will talk about the periodic table much more in Chapter 8, but we're building up to that. But we'll talk a little bit about today. And an electron is about 1/2000th the mass of a proton or a neutron. So electrons are not very massive compared to protons or neutrons. So I think that's another thing I take for granted, that I think everyone knows that atoms are made of protons, neutrons, and electrons. So those are these subatomic, less than atomic particles. So a neutron is slightly more massive than a proton. It also, the masses of protons and neutrons and electrons, but not as much electrons, they change by their environment. So depending on which atom they are in, they have more, or they have less mass, but than a free one. So bound protons and neutrons lose mass. And the charge, and we give the mass of a proton and neutron is about 1 atomic mass unit, and the charge +1 or -1 deals with a charge, the 1.6 times 10⁻⁹ coulombs. And the AMU, atomic mass unit, it's based off of carbon-12. I guess we haven't talked about carbon-12 yet. It's the isotope carbon-12. 12 grams of carbon-12 is a mole as well. Okay, so let's talk about elements, and this is a little bit more on the nuclear side. We tend not to write these as frequent in general, just chemistry moving around, but here I've written carbon, and this is carbon-12. So carbon, the bottom number is the atomic number. The atomic number is the number of protons. The number of protons of an element defines that element. Meaning, specifically, if an element has 1 proton, it's hydrogen. If it has 6 protons, it's carbon. If it has 26 protons, it's iron. And I know it's hard to see the small periodic table. I can't zoom in on this one. But this number here, like over iron, is 26. So that means 26 protons. So if you change the number of protons, the element changes. So elements are defined by their number of protons. And the top number for these is the mass number. That's the number of protons plus the number of neutrons for that specific nucleotide. And really, you don't even need to put 6 by carbon, because the element symbol C, carbon, implies then 6 protons. It's kind of redundant, although we tend to do it anyways. Then, okay, so I'm going to talk about isotopes. This is where Dalton was wrong. Remember, Dalton said that atoms are all the same for each element, and they can be different. So here, for instance, carbon has 3 common isotopes. Does anybody a fan of The Simpsons by any chance? What's the name of the baseball team for the Springfield? Don't know. Oh, Isotopes. Springfield Isotopes. Because of the nuclear power plant. So it has to do something. I think it has something to do with nuclear, and their symbol is the Bohr model. If you see the Bohr model is the orbiting electrons. Okay, so we've already stated carbon implies 6 protons. So every single carbon atom, doesn't matter the isotopes, will have 6 protons. Oh, and the definition of isotopes means same number of protons but different number of neutrons. And so a neutral atom has the same number of electrons as it does protons. So each carbon atom is going to have 6 protons. Later on, we'll talk about ions. Ions are, so maybe you heard the term charged atoms. That's an oxymoron. Oxymoron is when you have 2 things that are contradictory. Atoms are neutral. So a charged atom is an oxymoron, although it's still kind of proper usage, if you will, in English. But for these atoms here, they always have, atoms will have the same number of protons as they have electrons. Then for its neutral state. So, but the neutrons can differ. So the top number is the number of protons plus the number of neutrons. So to get the number of neutrons, you subtract the top number from the bottom number. 12 minus 6 is 6. Then for carbon 13, 13 minus 6 is 7. Carbon 14, 14 minus 6 is 8. So that means then, here are the different isotopes. Carbon has 3 very common ones, but they are the same with the exception of they have different number of neutrons. Of course, carbon 12 and carbon 13 are stable. 14 is an unstable isotope, and we give unstable isotopes the name radioactive. So carbon 14 will beta decay to nitrogen 14. So, so anybody have any questions of this? Okay. So uranium 290 or 238. Uranium 92 protons, 238 mass number. So this is my way of seeing if you're understanding what's going on. So I asked this question, and then I'm going to ask you to answer it, and just you to answer it by show of hands. This is my way of seeing it. Like I said, if you understand the material, if I need to explain it more. I should write a little better. Okay. How many people think A, there's 238 neutrons in uranium-238? How many think B, 92? C, 146? Oh, everyone's going for that. Good. You're doing much better than the noon class. I had to explain this again. So good job. That is the correct answer. Okay. Now I'm going to talk about the periodic table. Don't worry, I will talk about the periodic table ad nauseum in this course. You'll hear me say things so many times, you will partially get sick of it. So periodic table, what people usually say when they see this for the first time, although I'm assuming it's not your first time, but if it is, most people say, that's a funny shape. Number one. Number two is, what the heck is up with this step right there? Does that mean something? Okay, so let's talk about the funny shape. This is what the periodic table should look like. That's what it should look like. Because this goes right here. So, and this version of the periodic table, it's really long and skinny, and it doesn't fit very well on an 8.5 by 11 sheet of paper, and that's very close to the golden mean. And we like the golden mean because we think it's pretty. So what we've done is we've chopped off this portion and put it down there so that it'll make the chart look prettier. Okay? That's number one. Number two, what does that step mean? That means everything to the right here are nonmetals, and everything to the right, everything to the left are metals. And I know I will get to semiconductors in a second, or metalloids, which are kind of both. So metals and nonmetals have different properties. And generally speaking, nonmetals are insulators, meaning they do not conduct heat or electricity well. And metals tend to be conductors, meaning they conduct heat and or electricity very well. So to illustrate this point, my Apple Pencil here is made of plastic. I think it's polyethylene. So it's hydrocarbon, hydrogen and carbon, non-metals. Let's say that this board here had 10,000 volts on it. What would happen if I touched my non-metal pencil to this huge potential? Nothing. This is a brass key. It's made of copper and zinc, both metals. What would happen if I touched a potential with that? Yeah, I would get shocked. So metals tend to conduct electricity and also heat. If I stuck this into boiling water, took it out, and I touched my skin, it would feel hot. I stuck this into boiling water and then took it out real fast, it wouldn't feel hot. This is an insulator. This is a conductor. So also, if I were to take this key and if I hit it with put it at an angle and hit it with a hammer, it would just bend. If I did the same thing to the Apple Pencil, It would shatter. Why? Well, metals tend to be ductile, which means bendy. Non-metals tend to be brittle. So hard and brittle versus ductile, which means bendy. Is that true for everything? No, of course not. You'll learn this about chemistry class with me. What's the point of coming to class and hearing me say something if I don't contradict myself soon thereafter? There are usually exceptions to every rule. So carbon graphite, a non-metal, conducts electricity. Diamond does not conduct electricity well. It's an insulator, but diamond is a very good thermal conductor. So there are exceptions. DNA, the DNA molecule, all non-metals, conducts electricity. So, then there are these other elements that are on the line or on the step line that are kind of like both metals and non-metals. So this is Theodore Gray. This is the e-book version of his, he had a book that came out. And you can see the periodic table back there, the back classroom is the same one that I have here. You can get this app too if you want to spend $15. Let's look at the metals. And something to note here is sodium metal. And look at the color of sodium. Here is silver metal. Actually, well, that one's got some of the black oxide on it. Here's some polished ones. There you go. There's some polished silver. And let's look at, here's cobalt. So do you notice anything about the colors of all these things? They all look about the same, right? Metals pretty much look the same. There's a couple exceptions. Copper is the reddish color. Gold is a yellow color. And the oxide for osmium makes it look kind of blue. So the metal itself isn't so blue, but the oxide layer makes it look blue, and potassium looks kind of purplish with its oxide. So, but everything else, it just looks the same. It's just a silvery sort of metal. And then with that in mind, let's take a look at silicon. So here is some silicon here, and it looks really shiny. So silicon is shiny. It looks, I mean, just look at this, you're like, oh, what's that metal? If you feel it, it feels different than a metal. It's not ductile. If you hit it with a hammer, it'll shatter. So it's really brittle. But it looks shiny. The other thing, silicon, as is right now, silicon does not conduct electricity. So next semester, if you take this course, you'll learn about the valence band and conduction band. So if there's open energy levels right where the electrons are, then the material is said to be a conductor. So all metals are conductors. That means that, so silver is the most conductive metal of all the elements. So silver, gold, iron, whatever it is, even the combinations of them, like brass, they have the electrons. If you put electricity to it, it will conduct at any time. Insulators. So we humans are insulators. Supposedly, our band gap, the amount of potential it takes for us to be able to conduct electricity, is 60 volts. I still always disconnect my battery when I work in my car, and that's supposed to be 12 volts. But apparently we could grab both ends of a car battery and not get shocked. I still don't trust myself to do that though. So, what's that? Oh, you do?
Oh yeah.
Okay. It must be the oil. It must be the salts or something like that. I don't know. But or maybe you're more conductive than the rest of us. So yeah, I'd imagine. But silicon does not conduct at 0 volts. Silicon will conduct at 5 volts, though. So, and that's the basis of our binary code for computers. So no conducting at 0 volts, that's our 0, and conducting at 5 volts, that's a 1. And it uses something called TTL, transistor-transistor logic. So that's our 1s and 0s, is the fact that silicon will conduct at 5 volts and will not conduct at 0 volts. So our computer systems are based off of that, right now at least. So other ones, germanium is also a semiconductor. It looks like a metal, but I'm not as familiar with germanium. I've never touched it with my own hands. But, and arsenic too, that's one. Where's arsenic? It's the arsenic. It's pretty shiny. Beautiful, beautiful, beautiful death. Actually, tellurium's really, this stuff is really bad. One about toxic material. Oh, this wasn't a James Bond movie. This is Skyfall. You guys ever see Skyfall? They one of the ways they killed one of the people is they put tellurium and the on his cell phone, and so he was touching it. So then that killed him. So tellurium is one of the few substances. Well, I guess it's an element. It's one of the few elements that you can die by touching it, and it's not a very pleasant. It's hard to do. You'd have to touch it for a while. Polonium, if you touch that, you're going to die. But tellurium, you have to touch it a while. And apparently, you smell like garlic too. But okay. But so there are along the step ladder, there are the metalloids. So along here, you have elements that are kind of like metals and kind of like non-metals. So they're kind of properties of both. So next question is dysprosium, which is right here. What do you think? Is dysprosium, is this a metal? How many think it's a metal? How many think it's a non-metal? How many think it's a metalloid? So we're all over the place. Most people don't want to play. You guys don't want to play with me today. It's a metal. So everything, so here's a step ladder. Everything over here, and remember this part here fits in there. So the periodic table should look something like this. So this part here is right there. So and it's here's a step ladder. So everything over here is a metal. So and it's a specific type of metal that we call rare earths. These right here, the top one. Well, actually, I guess all of these, but we don't use. We tend not to use these in industry very much, except for maybe thorium. But the top are called lanthanides, and these are called actinides because this is lanthanum and this is actinium. But the lanthanides are also referred to as rare earths. If you ever heard that term before, they use them quite a bit in electronics. They're not really that rare, to be honest with you. This block in the middle right here, these are called transition metals, and a lot of the chemistry for the rare earths and actinides and transition metals, they don't fit all the rules we're going to talk about in this class. So there's different rules, different bonding rules mostly for them. So the trends that we'll talk about in this class work really well for the first two columns, and then this will erase this block here, the P block, the last two columns, or last 6 columns, sorry. And we give certain names to these. Again, I'm going to go over this ad nauseum. The first line here, we call these the alkali metals. So this name came from the alchemists. So if you are familiar with the book Harry Potter and the Sorcerer's Stone, that's actually incorrectly used. It's Harry Potter. It should be Harry Potter and the Philosopher's Stone. So they changed it to Sorcerer's Stone for the American audiences. If you look at the region-free DVD, like I bought that, and they say Philosopher's Stone, or whatever it is in Britain, Philosopher's Stone. But the alchemists, they believed that they'd had a series of experiments they would do, and they believed if you were pure of heart, you could create a substance called the Philosopher's Stone that could turn lead into gold and give you and generate the water of life. It'll give you eternal life. but they named many of these things, and they did chemistry experiments of sorts. Names can vary by language as well. So, for instance, like iron, Fe, we call it's iron. In Hungarian, it's var. There's nothing sounds like nothing, right? And tungsten is named in German. It's wolfram. In German, we call it tungsten. Uh, and and in Latin, Ag is argentum. In Spanish, it's plato. In English, it's silver, right? And in gold English, it's aurum in Latin, oro in Spanish, and jing in Mandarin Chinese. So I mean, and then in Hungarian, sodium is natrium, and and in whatever in Hungarian. So I mean, the names of the elements are going to be different in different languages. It doesn't necessarily mean anything. Now, and also they were named throughout history. Now we have a naming board. It's the it's the I forget the name of it. Shoot, it's in Columbus, Ohio. They name everything, and of course we're up to element number 118, and pretty much so. I mean, if you discover it, you get to name it. For instance, that's one of the general rules. But I mean, like potassium also that was named in Arabia, so there's not really any 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 one place that we could say named a lot of elements. Well, I guess you could say there's a couple. There's my alma mater. We have californium and berkelium. That's from California, Berkeley, of course. Many of these plutonium, these were all discovered in Berkeley. Some of these, like Einsteinium, they discovered those after an atomic blast. They blew up a hydrogen bomb, and then they sent a plane to collect the dust, and they found some of these other transuranic, so after uranium elements there. But okay, let's go back to the names here. So the first column of the periodic table are called the alkali metals, and alkali. The word alkali, alkaline, means basic. Means the opposite of acidic. So like an alkaline battery means the center of the battery is basic. It's not an acid. Versus a car battery is a lead acid battery. Those are acid batteries. So alkali metals means if you throw them into water, they form bases. And then the next column are the alkaline earths. Alkaline earths. Pencil's not working as well. The alkaline earths there, if you take those metals and you throw them in the water, it forms a basic solution. Basic meaning not acid. Then why is it called alkaline earths? So alkali metals, the first column, are very soluble. They dissolve in water very well. Alkaline earths tend to be less soluble. So if you start mixing things, you get precipitates, which means new compounds form and they fall to the bottom. And remember the earth, wind, fire, water idea of the elements? That means you have water that has some earth in it. And you can do experiments to extract the earth. So that's where it's like, we made an alkaline solution, but it makes dirt. So we're going to call these alkaline earths. That's where that name came from. This column of the periodic table here, these are called halogens. A halogen is Greek for salt forming. So halogens make salts. So what is a salt? Acid and base. So acids have one set of properties, bases have other sets of properties. We'll talk about that, and if you keep on coming through, so not everybody has to take Chem 162. We'll talk about acids and bases quite a bit there. But acids taste sour, so like lemon juice, it's very sour. Bases taste bitter. What's a bitter flavor? Like if you buy cold medicine that's generic and doesn't have any sweeteners added to it, like from Walmart or something like that, and you buy like Welltussin versus Robitussin, you take that, and it says that, or like generic NyQuil. You ever drank that stuff? You're like, ah, that's That's bitter. That's because things that are alkaline, that are bitter, tend to be poisonous. So caffeine is bitter, for instance. Caffeine is very poisonous. Uh, but I mean, people are like, I drink it all the time. Yeah, you drink 100 milligrams of it, right? Milligram. If you took like 3 grams, your heart would explode. So nicotine, it's also alkaline. Things like that. That's very poisonous. If you dip your hand in pure nicotine, you can have various physiological effects. So we as humans, we hate basic things. They're poisons. So what about salt? How does salt taste? Salt tastes salty, right? It's not an acid or a base. So like sodium chloride, you can take hydrochloric acid and mix it with sodium hydroxide. So acid plus base makes a salt, and the salt no longer has the properties of an acid or a base. So halogens make salts. And then we have the noble gases here, last column. Noble gases, they're called noble. They used to be called inert gases because we thought they didn't react. It turns out they do react, they just tend not to react, and we give the word noble. This is like the old English term, like the nobility. The nobility were very stoic. So they'd be like, I'm a king, and today is the worst day of our lives. I'm just using the royal we. Our life is very happy right now, and our life is very sad. I went through a crisis just now. Because I'm noble, you can't see it. I'm very stoic. Then you have the commoners that are very reactive. You know, where like, oh, it's common of you to get angry and show your anger. You need to be noble about this. So that's the noble gases. They're unreactive, unresponsive. So also when things bond, so atoms will bond with other atoms in a fashion that actually brings them like noble gas configuration. So meaning the electrons are 2, 10, 18, 36, 54, 86, or 118. So those number of electrons tend to be low energy. So so right now everyone is sitting down. No one has come up and asked me like, hey, is it okay if I spend the class doing push-ups? Or can I do jumping jacks for the entire class period? You know, why don't you want to do push-ups for the entire class period? Because it takes energy, right? You'd rather be sitting down. If we were here for 10 hours, you'd probably ask me if you could lie down, right? So if you're going to do something for a long time, you like to be as low energy as possible. Electrons are the same way. They want to be as low energy as possible, so they will bond to be lowest energy. And if we were to go on and study quantum mechanics, you could do all the calculations, and you will find out that 2, 10, 18, those numbers of electrons tend to be very, very low energy. So they're a local minimum in the potential energy diagrams. There are other local minima. We will not talk about them in this class. So the transition metals and the rare earths can bond in fashions that are different ones. We'll talk about a little bit about some of that in chapter 9. There are some breaking of those rules, but it tends not to happen that way. And again, I'm talking about some things. Then I'm contradicting myself. The thing is, chemistry is an observational science, so we see things, we observe on them, and then we report it. So you'll notice that we have general rules, and we have exceptions to those rules, and we have exceptions to those exceptions, and maybe with some special cases about that. And that's just because we're describing the universe the way we see and observe it, and we've come up with these rules to describe it. So it's not me trying to mess with you. So it's just the way things are, and this is how we observe and report them. I mean, if we went through and did the quantum mechanics, and if I let you guys go through lots and lots of math, and then we did lots of quantum mechanics, we can do this. We can derive these rules using math and physics, but and then you can see the math behind it. But for now, I think it's probably easier just to look at the rules. I tend not to, like, it takes a long time to do those calculations. You need like a supercomputer and lots of time to do that. But, oh well. let's go back and talk about bonding. So we talked about how things like to be like noble gases. Atoms will tend to bond to have the same number of electrons as noble gases. And one of the easiest ways for them to bond is for one atom to give electrons to the other atom, and different ions will form, and then they will be attracted to each other by the Coulombic force. The unlike charges attract. So positive ions, an atom will become a positive ion by losing electrons. So remember, if you change the number of protons, the element's identity changes. So carbon, if carbon wants to be a +1 ion, it will lose an electron. If carbon has a proton added to it, it will now become nitrogen, a new element. Elements are defined by the number of protons. So ions are formed by transferring electrons. So positive ions lose the negative electrons, and then they become cations. And you can remember cations, think of the T as a plus sign. So the cation, the T in the cat is the plus sign. So if you forget that. Negative ions gain electrons. So if an atom gains electrons, it becomes a negative anion. So let's see if you're following this. So uranium-238 plus 6 ion, how many electrons does this ion have? How many think it's 146, 92, 98, 86? We have half for 98 and half for 86. So cations lose electrons. So how many protons does uranium have? Uranium neutral, how many does it have? 92. So to become a +6 ion, what has to happen? 6 have to be removed. So it's 86. Does that make sense? Okay. How about oxygen -2? How many electrons does this have? How many think it's 8? How many think it's 10? All right, good. Everyone's going for that. It is 10. You got it. All right. So let's talk a little bit about elements and life. There's a whole field involved in this, field called astrobiology, trying to think about how we can discover life outside of the Earth. So we've already started looking on Mars, and we're wondering if there's life on Europa. Europa is a moon of Jupiter. It's got lots and lots of water. Maybe Titan has life. We don't know. We'll see. We're wondering if there's life outside the Earth, at least even within our own solar system. So, but we're also said to be carbon-based life forms. So if you look at the way we are, so this is humans' composition. Oxygen, 65%, 10% hydrogen, 18, so 1/5 carbon, more or less. But then you look at the number of atoms, we are 26% oxygen and 62% hydrogen. So why is this not surprising by the atom percent about oxygen and hydrogen? So what are we said to be mostly made of? Water. Yeah, there's a lot of water. Not all of this is tied up in water, but I mean, we have lots of water in our bloodstream and our cell cytoplasm. We're made of cells. There's lots of water inside and outside of our cells. So not too surprising there. But we're called carbon-based. Why carbon-based? Oh, and we also give the elements, they say, we're looking for CHON or CHON, just because that kind of, I mean, it should be hydrogen, carbon, oxygen, nitrogen, but the HACON sounds better than, or CHON sounds better, HACON. That's kind of like, you know, anglifies kind of like the word a little, or the 3 element, or 4 elements. And why is nitrogen? Nitrogen is only 3%. Why is it included? It's in amino acids and nitrogen bases. So for DNA, for bases that are involved, and they are bases, they are alkaline, and also the plant materials, alkaloids, nicotine and caffeine are alkaloids. They're alkaline things generated by plants. So Again, it has the word alkaline in it, alkaloid. Nitrogen is in those, and in amino acids, so for proteins. So nitrogen, even though it's 3%, it's pretty important. But we're called carbon-based because carbon's a very unique element. I used to do research with carbon, and if you were to throw carbon into a vacuum chamber and blast it with electricity or blast it with a laser, carbon will tend to form straight chains. So carbon is a unique element by the fact that it forms really, really long straight chains. For instance, silicon, people say, oh, we could have silicon-based life forms. No, you can't. At least not life as we know it. So silicon, if you throw a bunch of silicon into a vacuum chamber and you zap it with a laser or electricity, you will, well, silicon itself, you have to use something like silane, SiH4, and you could then zap that with electricity. That would then form different clusters of silicon. Below 19 atoms, silicon tends to form prolate football, like American football typed molecules or clusters. And after 19 atoms, it tends to form more spherical, like called cage-like structures. It's like kind of just, they're spheres, more or less. And then they just keep on growing like bigger and bigger spheres. Whereas carbon tends to form chains or chains that have chains attached to them, kind of thing. So many of our structures, like DNA and like the cell membrane, a phospholipid bilayer, so which has like on the order of 25 carbon atoms on it. So that 25 carbon atoms, really easy to make a straight chain. Whereas silicon, it would just be a blob. So it's unlikely that we will find life as we know it. That's not carbon-based. Maybe there's a way like the synthetic motor oils or like the synthetic like the conditioners that use silicones or caulking silicones. You can have silicon branching with oxygen, branching with silicon. That will form a straight chain. And then you can also have carbon attached to those chains as well. But the other problem with those is that the silicones are very unreactive. So I mean, that's the reason why you put it like the caulking or something like that around a bathtub, because it's unreactive. And the same thing with the motor oil. It's less reactive than carbon. So doesn't. Oh geez. Oh. Got it. doesn't react as much. So, but we still want the materials to be reactive, so we can do chemical reactions with it. So, but who knows? Maybe there is a planet out there that has silicone-based life form instead of silicon. But okay. So that's what we see in life, and these are the elements we're looking for. And we're also looking for planets or areas that you could have liquid water. So that's another thing. And we're actually finding that planets being in the habitable zone where there's liquid water are fairly common. So we haven't discovered life outside of the Earth yet, but we'll see. Okay, changing topics yet again. Let's talk about the periodic table. And here's chlorine with 35.45. And I've talked all about the mass number. And you're like, okay, and if you look at the periodic table, you look at things like hydrogen here. The bottom number is 1. You're like, all right, I can deal with that. Carbon, it's 12. You know, I'm okay with that. Nitrogen is 14. Then you get to copper, you're like 63.5. You're like, uh-oh. What's going on here? What the number is on the bottom here, this number here is called the atomic mass, or sometimes the atomic weight. We use weight and mass interchangeably very frequently. The atomic mass, it's the terrestrial, meaning Earth, the Earth average of all the different isotopes. So for instance, chlorine is about 1/3, it's about 1/4 chlorine 37, and it's about 3/4 chlorine 35. So if you were to look at a mass spectrometer of chlorine, you will see something that looks like this. And this is 35, this is 37, where you have a peak that's at 35 charge to mass ratio that's 3 times the size as 1 at 37. Okay, so that means that the ratio is about 25% chlorine 37 and 75% chlorine 35. And like I said, that's true for here on Earth. Now, in different planets, moons, stars, you can have, well, stars are just kind of big balls of gas or plasma. But if you were to look at the isotopic ratios of the elements on the moon or Mars, it's different than the Earth. So maybe you've seen the news like, oh, we found a Martian meteorite. How do we know it's from Mars? It's from, well, I guess we're still kind of hypothesizing that it's from there, but it's because of the ratio of the isotopes, this difference. We have been to the moon, and we have brought moon rocks back, so we have looked at the isotopic ratios, and they are different than the Earth. So some are the same and some are different. And from that we part have you heard of the collision theory for the formation of the moon? So yes. We think the moon came from a collision between Earth and a Mercury-sized planet that struck, and then material was spewed off of both the Earth and then the other planet-like object, and well, I guess it would, I don't know if it would be like or whatever, the other large object, and then the molten material then congealed to form the moon, and then as it cooled though, and there was no geological activity as it cooled. Well, it cooled as it was cooling. By the Earth's gravity, it got pulled towards the Earth. So the moon is tightly locked to the Earth, meaning we can't see the other side of the moon, the dark side of the moon. So you can only see the front side. But if you look at the material on the moon, some of it is Earth-like, some of it is not Earth-like. So that's in part where we form that theory. But here on Earth, we have there's a few examples but they tend to be, this is mostly true, that the isotopic ratio for all the elements is more or less the same on Earth. And the way we figure out the atomic mass is by taking that average. So, for instance here, well, okay, so you look at this equation here, atomic mass is the sum of each fraction of the isotope times the mass of that isotope. So let's apply that here. So copper has 2 isotopes. So one is about 63 AMU, has a natural abundance of 69%, and the other one has a mass of about 65 with a natural abundance of 30%. What is the atomic mass? So we're going to apply this equation to here. So the fraction of 1, so it's 0.6917 times the mass, 62.9396, and 69% is 0.69. So it's taking the percent trying to do a fraction, plus 0.3083, that's 30.83%, times 64.9278 atomic mass units. And I actually had this before, so I can show you this. The calculator, throw in your calculator, and you get 63.55 by 4 sig figs, the sig figs from the percent. 63.55. So does this make sense? You're just applying that equation there for the percentage, the abundance times the mass, and then summing it together to 100%. So, questions with this? All right, next concept, the chemist's dozen, the mole. It's referred to as the chemist's dozen. We use different, like colloquially we do this. Like I remember back when I was in college and I was in a fraternity, we would judge how crazy a party was by how much beer we drank. So like if it was a 10-case party, it was kind of an okay party, but if it was like a 50-case party, like, ooh, that was a crazy one. Or you could do it by kegs. We were not allowed to have kegs on my campus. So at University of Dayton, you're not allowed to have kegs. But like if it's like 2 kegs, like, man, 10 kegs, whoa! You know, that's a huge party kind of thing. So, I mean, but a case of beer, that's 24 beers. You know, you didn't say, well, how much alcoholic beverages did you consume at said party? Was it 1,000 beers? You know, no, we'd be like, all right, it's like a couple cases, you know, kind of thing. So right, we also paper. When you buy paper, like a ream of paper, that's 500. The little stack is 500 sheets of paper, and like I wouldn't go to the department secretary and ask her like, hey, can I get 2,500 reams or sheets of paper? You know, she'd be like, well, how many reams is that? Is that a box of paper? Like, you know, the box is like 10 of those reams, I think. You know, like she'd tell me to like, oh, you know, give me something I can work with, like a box of paper, right? I know what a box of paper is. You can buy them at Costco, kind of thing, you know, or Office Max. So we take things and we can put bigger numbers to it, and then we can apply it that way. So, or you can even take fractions of that. Can I get a half a box, or can I get a half a dozen? I don't say 6, I say half a dozen. Half a dozen eggs. I don't say 6 eggs. You know, can I get a dozen and a half? That's what I get at Costco. Or can I get 3 dozen eggs? You know, kind of thing. So same thing. We have a dozen of sort in chemistry. We call it the mole. And the mole is based off of carbon-12. So 12 grams of carbon-12 is a mole of carbon atoms. So that's what we're based off of. We might change this soon, within the next decade or so, to be based off of silicon. But right now it's still carbon. So our chemist does, and it's 6.02 times 10 to the 23rd, thereabouts. And that's this number here. So, and hopefully 2 thoughts run into your mind. The first one is, that's a really big number. That's a really, really big number. And the second thing that should run through your mind is like, man, atoms must be really tiny. So yes, atoms are very, very tiny. So we need a huge number to be able to make sense with them. Just because we're not used to counting things one by one to 602 times 10 to the 23rd, or 6.02 times 10 to the 23rd. So, and then before I get to the next problem, you can see here, let me teach you something called dimensional analysis. I'm sure you've probably seen this before. Anybody know how many seconds there are in a year? Anybody have this memorized? How many seconds are there in a year? Anyone know? We can figure it out. We can take 1 year and we can multiply it by 1 a bunch of times. So I can take a year and I can multiply it by 1. I mean, I know it's not exactly 365, but 365 over a year, this is multiplied by 1. And there are, in fact, 24 hours a day, at least there was in about 1980. Days are a little longer now. Days are getting longer as we speak. From the moon, thank you, moon. 60 minutes in an hour and 60 seconds in a minute. This is so from our Babylonian friends. They came up with this idea from the base 60. Those are exact numbers. There is, in fact, exactly 60 minutes in an hour and 60 seconds in a minute. The number of hours, the time of a day varies. There's a little bit of uncertainty, and it's getting longer. And the length of a year it's pretty stable, but it's not. It's about a quarter of a day longer, but not exact as well. So sometimes they put leap seconds here and there, and if you ever see that in the news, like, a leap second was added to the atomic clock today. So, all right, but what I'm trying to say here, though, is that you can take a number, you can multiply it by 1 a bunch of times, and then come up with a different unit. And the units cancel, too. So years cancel, days cancel, hours cancel, minutes cancel, right? And we're left with seconds. So, and this is called dimensional analysis. So we can do dimensional analysis, calculate the number of copper atoms in 2.45 moles of copper. So you start off with 2.45 moles copper, and then so it is 63.55. Is it 60? Yeah. 63.55 grams of copper, 2 moles of copper. And I'm using this this plus like the box there, just because it's easier for me to write that way. So it's nice and neat and easy. I'm saying the top lines are multiplying and the bottom lines, top lines are being multiplied, bottom lines are being divided. So, and we just figured out in a previous example, it's 63.55. If you don't remember that, you will always have your periodic table accessible to you. You do not have to memorize the periodic table, but I can see it fine. Maybe you, depends on how good your eyes are. This says 63.546 right there. So I will never ask you to memorize the molecular or the atomic mass of copper. But here then we're applying dimensional analysis, and oh geez, I got this backwards. I didn't need to do that. I'm sorry, I did not need to do that at all. Sorry. 6.02 times 10 to the 23rd atoms. Sorry about that. I jumped ahead of myself. So a mole is 6.02 times 10 to the 23rd. So you can just apply that there. There's another example that we go over that has copper in it that has the mass. Sorry about that. But if you put in your calculator, that's what you'll get. You would get 1.47 times 10 to the 24 atoms copper. And another thing to note, I'm going to zoom in on my calculator output there. So you'll see this key on your calculator. It says EE, at least on the Texas Instruments. I don't know what it is in the other ones. The EE button means times 10 to the whatever. So so right here, this is then Avogadro's number. It's 6.02 E, that means times 10 to the 23rd. So use the EE button, the capital E, do not use the lowercase e, that is Euler's number, which is a different number. That will not give you the intended result. Okay, so let's see if you are following. So how many oxygen atoms in half a mole of O2? How many think A, half a mole? How many think B, 1 mole? How many think C, a quarter? And I think D, 2. Okay, so the people that have participated did say 1. This is the correct answer. So O2, this 2 means two atoms of, I just OX for oxygen. That subscript, like if you see something that says H2O, the 2 in the bottom of H implies 2 of the atoms, the subscripts. And then if there's no subscript, it implies 1. So like glucose, that implies 6 atoms of carbon, 12 of hydrogen, and 6 of oxygen. Okay, so this is kind of a trick question for you there. So the half a mole there's half a mole of O2, but there's 2 atoms in each. So it's kind of like saying how many eyes, so I know people don't have to have 2 eyes, but most people have 2 eyes. How many eyes does half a dozen of people have? And it's a dozen, right, because each person has 2 eyes. So half a mole of O2 has 1 mole of O. Okay. And let's look at another thing here. So calculate how many moles in a 0.265 gram pencil. So we have 0.0265 grams carbon. And when you get this problem, you also have to look at what information is given and come up with a plan. The mass is given, the identity of it is given, and where do you want to go? We want to know moles. So we're given the identity of the substance, we're given the mass of the substance, and how do we get to moles? Well, you have to remember, like, oh, periodic table, and then the bottom number here is the atomic mass. And from that, if I divide by that, I know that 1 mole of carbon has 12.01 grams of carbon. And I think it's still in my calculator from last class. Let me see. And it is 0.00221 moles of copper, or carbon, copper. Keep on saying copper. Does anybody want to see the calculator? I can take a picture. Anybody want to see it? Okay. All right. And what about other ones, a little more complex? How much copper is in a penny with 3.1 grams? This is where I need the 63.55. So we could have one with more than one step. 3.10 grams copper. I usually wouldn't write the 10, but since I just covered sig figs in lab, I'm trying to be a little more explicit. So one of the knee-jerk reactions I'm trying to train you is to start thinking in moles. So how do we get from mass to atoms? Well, we can calculate the moles, and then we can calculate the atoms. So then for every mole of copper, we need 63.55 grams of copper, and then 6.02 times 10 to the 23rd Cu atoms per mole of copper. Again, these units all cancel, so grams carbon, copper sheet. Grams copper, moles copper cancel, and this I normally don't prep it like this, but I couldn't figure out how to erase these, so I just put white over it. And then putting it this way, you get your calculator, puts it in the calculator. The other thing to note is that I oftentimes see mistakes, so I've been teaching for 13 years. The mistakes I see frequently are in order of operation. So we'll go over this, again, quite a bit. But this one's pretty straightforward because you have multiplying all the way, like 2 multiplying on the top, and there's 1 dividing. Sometimes if I had 1 on the bottom, let's say this was, well, so 3 times 4, 3 times 6, actually maybe that'll be different. So 6 times 2 divided by 3 times 4. So if you have a problem like this, we have 6 times 2 divided by 3 times 4. Sometimes people will write in the calculators 6 times 2 divided by 3 times 4. The problem with this is that going left to right, you would have to put the parentheses over this one. So, and again, we have, this is a smartphone, but it doesn't have the ability to do math. It only can do what we tell it to do. AI right now cannot solve chemistry problems. So chemistry is a solely human endeavor right now. So Google, for instance, like if I ask Google to solve this problem, Google actually probably could solve this problem because this is a textbook and there's probably an answer some out there you could search for it. Let's say that I made it 5 grams instead of 3.1. Google couldn't solve this. The AI that runs Google couldn't solve this. Watson, the AI that beat people on Jeopardy, couldn't solve it either. We don't have computers don't have the ability to think outside of what we've prescribed for them. So a human could do this relatively easily, though. So as of right now, maybe in the future AI will become more intelligent, but right now it's only a human endeavor, and such that our tools that we use are dependent on a human to input it in. And the order of operations are parentheses happens first. I should put, careful, this is not equal to that. Parentheses happens first. Exponents and logs happen second. Multiplication division happen third. addition, subtraction, fourth, and it goes left to right. So if you put in your calculator, you have to be mindful of where it goes. So that's the majority of the mistakes I see is actually order of operations. And class time's over, but let me say how many oxygen atoms are there in 16 grams of oxygen? 16 grams of oxygen is in fact 1 mole, which means it has that. So, but we are now done with chapter 2. So, oh, and Monday is a holiday. So, if you come to school, you'll be locked out. So, all right. See you guys later.
So is the lab
Yeah, labs do the following.
the following?